Okay, welcome to Robotics 1, and today's date is 10/6/20. In today's class, I am going to go straight away in solving a simple problem using MATLAB. Uh, it's a robotics problem. So far, we have worked out lot of forward kinematics problems, so it should be very simple for you guys. So what I'm going to do is think about it that I have a robot, and this robot is a simple 2 degree of freedom robot. And in this 2 degree of freedom robot, I have a revolute joint, and then I have a prismatic joint. This is a simple case. So I have a revolute joint and I have a prismatic joint, and this is where my end effector is. And what I want to do is, in this simple problem, I want to set up the homogeneous transformation matrices. After the homogeneous transformation matrix is done, I have to work out the forward kinematics. And then I want to use the MATLAB to find out the Jacobian in the translation and Jacobian in the rotation. So let's see. The way we are going to do it is step number 1, set up the coordinate system. And this is going to be my z naught. This is going to be my x naught. And this is going to be my y naught. Next thing is I need to set up x1. Let's set up the z1. So my z1 is going to be like this. My z1 is going to be like this. And since my z1 is like this, my x1 has to be perpendicular to z0 and z1. And the most logical way to draw x1 is this. And then construct the triad. And then you will realize this is going to be my y1. So I have x1, y1, z1. And for the sake of simplicity, I will replicate c1, y1, x1. And now I would give you some distances. This distance I'm going to call as A1. This distance I'm going to call D. This distance is D2. And for this simple 2 degree of freedom robot, so this is 2 DOF robot, I need to do the homogeneous transformations. So first, let's find out. This would be my theta 1. So 0 H1 needs to be found out. So I'm going to do 0 R1. To find 0 R1, it's simply cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1. Next thing, multiplied with a projection matrix. And this projection matrix is in between x1, y1, x0, y0, z0, x1, y1, z1. So you can look it up. Projection of x1 on y0 is 1. Projection of y1 on z0 is 1. Projection of z1 on x0 is 1. Which means my homogeneous transformation matrix is going to be a product of these two matrices. First row, first column. First row, second column. First row, third column. Second row, first column. Second row, second column. Second row, third column. second row third column is sine theta 1, third row first column, third row second column, third row third column, and the last is 0 0 0. And now px, py, and pz, the distances in x0, y0, and z0 direction. Distance in x0 is 0, distance in y0 is 0, distance in z0 is a1. Now the next thing is I need to find 1 R2. Now please note 1 R2 is a prismatic joint, and for the prismatic joint the rotation matrix is 0 1 0 1 0 0 0 1 0 0 0 1. This is the rotation matrix, but please recognize that you will have to take into account the projection matrix as well, and the projection matrix here will be between x1 y1 z1 x2 y2 z2. Please note, yeah, 0 1. So this is 1 0 0 0 1 0 0 0 1. So my homogeneous transformation matrix 1 H2, this homogeneous transformation matrix is going to be 1 0 0 0 1 0 0 0 1 0 0 0 1, and then I need the distances along x1 y1 and z1. So if you look at the distance along x1 is 0, distance along y1 is 0, but distance along z1 is d2. So now I have these two homogeneous transformation matrices, and what I need to do is I need to find 0h2. 0h2 is 0h1 1h2. And now what I'm going to do is, there is something else I just want to tell you at this point, is since we are going to solve for the Jacobian, since the purpose is that we need to use MATLAB to solve Jacobian, MATLAB for Jacobian, it might be a good idea to have 0R1 and 0R0 matrix already determined. The good news is 0R0 matrix is an identity matrix, and 0R1 matrix is nothing but the 0R1 matrix that we already found out over here. So we have these two matrices. Now what we need to do, here is the process. So first find out 0 H2, and once you find 0H2, you are going to have a big matrix, and then you are going to have Px, Py, Pz. So you are going to have Px, Py, Pz. Then there will be bunch of zeros here, and you are going to have a rotation matrix over here. So we are going to grab Px, Py, Pz from this matrix. So Px, Py, Pz from this matrix, and then going to use the command in MATLAB, which is called Jacobian. So this command, if you have MATLAB 2020, the command is Jacobian. And in the Jacobian command, what you have is, in parentheses, first you will have to enter Px, Py, Pz, and then you have a comma. Yes, 0R0 is always identity. 0R0 is always identity. So, and then here we need to enter the joint variables, and joint variables here are th1 and then d2. And once you do this, MATLAB will give you Jacobian directly. So there are, if you want, you can do what we did in the last class. You can manually differentiate and find the matrix, or you can just use the MATLAB command Jacobian, and then Jacobian will be computed. This is for the translation. So this is for translation. Now let's look at the Jacobian for rotation. The Jacobian for rotation is given as omega x, omega y, omega z. And unfortunately, there is no shortcut technique for this. What we will have to do is, we have to say 0r0 multiplied by the joint variable about z0 plus 0r1 multiplied by the joint variable. Essentially it is the angular joint variable, so this is angular variable about z1. So this is the process that we are going to follow. This is a simple problem, so it should be fairly straightforward. And once we are comfortable with this problem, I'm gonna go back and look at the problems that we already solved. Believe it or not, we have worked out forward kinematics for about 15-20 problems and inverse kinematics for about 5-6 problems. So we can look at some of those problems, but use MATLAB to find Jacobian, and it's very quick. So now I'm gonna change my display to MATLAB. Okay, now you should be able to see my MATLAB window. And what I'm going to do is, I'm going to first program 0h1. Actually, let's start from the beginning. I would say SYMS because we are going to do a symbolic transformation. I would say TH1, that corresponds to for theta 1. And then I'm going to call D2. So I have TH1 and I have D2. Then what I'm going to do is, I'm going to say 0h1 that we already computed, which is minus sine th1, 0 cosine th1, 0 semicolon cosine th1, 0 sine th1, 0 semicolon 0 1 0 a1. So I need to say a1 also as a symbolic variable. And then the last column 0 0 0 1. So this is my 0h1, 1h2. Yeah, I need 1h2. 1h2 is 1 0 0 0 0 1 0 0 0 0 1 d2 0 0 0 1. and 0h2 is equal to 0h1 1h2. So let's see what we get. 0h1. Oh, yeah, MATLAB will not like it. So it's h01, h12, h02. MATLAB doesn't like 0 before variables. Yeah. So this will be 0 h1 and 1 h2. Okay. So now this is what we have. And please notice I got the expression for 0h2. Now this is my px. So what I'm going to do is I'm going to write px is equal to copy, and I'm going to paste it over here. Then I'm going to do py is equal to copy and paste it over here. And I'm going to say pz is equal to a1. And then the command is, if you want to find out the Jacobian, the command is Jacobian in the parentheses square bracket px comma py comma pz square bracket complete semicolon. Now the variables that you need, and the variables, the joint variables are th1 and d2. And what you do is run this, and here you have your Jacobian. So as you can see, MATLAB gave us the Jacobian, and this Jacobian can be used in our further calculations. So now I'm going to shift to my iPad, but before I do that, I just want to make sure that everybody was able to get the Jacobian. Now, one important thing about this robot is, I don't know if you noticed or not, robot does not have any velocity in z direction. I don't know if you just take a look at the robot, and you would observe this robot can rotate around z naught, but unfortunately there is no motion, there is no translation around that direction. And that is the reason why the last column of this Jacobian is 0. Please note, this Jacobian is not a square matrix, it's a rectangular matrix. And now I'm going to switch back to my iPad. So we are back on the whiteboard. Now what I'm going to do is I'm going to write down the Jacobian that we obtained from MATLAB. So Jacobian that we obtained from MATLAB is of the form minus d2 sine theta 1 cosine theta 1 d2 cosine theta 1 sine theta 1, 0, 0. If you want to find out the joint velocities, here is what you do. You say px dot, py dot, pz dot, which is nothing but the velocity of the end effector in the zeroth frame, vy, vz. And I need to write this down. This velocity is in the zeroth frame is equal to this multiplied by the joint angles, which is theta 1 dot, the derivative of joint angles, and d2 dot. So these are the joint velocities. And this is how, and this guy is the Jacobian. Now, if I want to find out the Jacobian for the angular velocity in this problem is fairly simple. Here is the reason why. I want you to focus on equation 2. So I want you to focus on equation 2. In equation 2, what we are doing is we are substituting. Is a1 not considered? Yeah, a1 is a constant. Yes, because a1, if you think about a1, is the fixed distance between the zeroth frame and the first frame. And that distance is not changing because there is no prismatic joint that would extend. So a1, the derivative of a1 is actually 0. Any other questions? So here in this particular problem, the angular velocity Jacobian is super simple, because please note, you need angular variable, the variables correspond to the angular joint variable. So you need angular joint variable. The first angular joint variable is theta 1 dot. But you do not have second angular variable because second joint is a prismatic joint. So what you have here is you have a prismatic joint. So this is a prismatic joint. So you are just going to have omega x, omega y, omega z is equal to 0 r 0, and then you will have 0, 0, theta 1 dot. And this is going to be identity matrix. So omega x, omega y, omega z is going to be an identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1 multiplied by 0, 0, theta 1 dot. In other words, omega x is equal to 0, omega y is equal to 0. You are just going to have omega z is equal to theta 1 dot. Now, what does this mean? And this is the reason why we took this simple problem, is I want you to look at the physical the configuration of robot. If you look at the robot, the only rotation that is possible is about z naught axis. So this robot can only have rotation theta 1 dot about z naught axis. Next joint is a prismatic joint. This prismatic joint is not going to incorporate any rotational motion. There is not going to be any angular variation. There could be some linear variation, which means the actuator could get extended or retracted, but there is no rotation. So to speak, let me show you the inertial axis, which means the zeroth frame axis. The zeroth frame axis in this problem are Z naught, X1, X naught, and Y1, Y naught. So please note, there is no rotation here, no rotation. There is no rotation here, no rotation. The only rotation that is possible is about Z naught. And that's why we just have omega Z is equal to theta 1 dot. There is no omega X, there is no omega Y. Everyone understood? Any questions here? So this is how you would solve the problem. Now what I'm going to do is I'm going to take second problem. So in the second problem, this is actually we solve this problem for inverse kinematics. So now what we have here is we have a revolute joint. Then there is another revolute joint. And then this revolute joint has a prismatic joint. So you have R, R, and you have P. And now what we want to do is same thing, use MATLAB to find Jacobian. And the steps are, first, assign the coordinate system. This is Z naught. This is X naught. This is Y naught. Then you have Z naught. Then you need an X, which is perpendicular to both of these. So this is X naught. And then you're going to have a Y naught. So X, Z, and Y. I think when I worked out the problem before, X naught, yeah, I think I use the same coordinate systems. So this is X1, Z1, Y1. However, here I'm gonna have Z2. Now I need to have X1 or X2 that would intersect. And please note, unfortunately, in this problem, you can have two options. You can have X2 in this direction, or you can have X2 in this direction. But in both cases, you are not going to satisfy the four rules. So the easiest way is to use X1 or X2, sorry, X2 like this. And please note, X2 is intersecting Z2, but it is not intersecting. So please note, X2 is perpendicular to Z2 and Z1. X2 intersects Z2, but X2 does not intersect Z1. So that means, shouldn't X1 be rotated? Let me see. Z1. Yes, you're right. You are right. So this should be X1. So Z, x, then y will come down. Yeah, y1 will come down like this. Okay, just make sure that my coordinate systems are consistent. So y is going down, z is coming in. Yeah, so this is correct. Now z2 is x2 is perpendicular to z2. Okay, so now I have z2, I have x2, so z2, x2, and I have y2. So this is my y2. Okay, and then the last but not least, this is going to be my end effector frame. This is going to be y3, x3, and z3. Okay, are we good with the coordinate system? Now, next thing what we need to do is we have worked out this problem in the past. We have worked out this problem in the past. So what I'm going to do is I would actually utilize the homogeneous transformations that we used before to solve the problem. So first step is we need to find 0h1. We need to find 1h2, and then we need to find 2h3. Then finally we have to find 0h3, which is 0h1, 1h2, 2h3. Then we have to find out px, py, pz from 0h3, and then use the Jacobian command. Since we need to find out the Jacobian for the rotation, let me write this equation down first so we know what we need. So omega x, omega y, omega z. Please note there are two rotational joints. One first rotational joint and the second rotational joint. So I need 0 r0, 0, 0, theta 1 dot, plus I need 0 r1, 0, 0, theta 2 dot. And please note the next joint is actually a prismatic joint. So let me still write this down. 0 r2 is 0, 0, 0 because it's a prismatic joint. So now what I'm gonna do is I'm gonna go back to MATLAB and I will try to work out this problem real quick. The only thing what I want to check is in the previous problem, if our coordinate system is same as this coordinate system, we worked this problem before. If someone can quickly check that when we did the inverse kinematics on this robot arm, if the coordinate system that we used is exactly same as the coordinate system which is shown over here. Just please look at the inverse kinematics lecture and then see if the coordinate system is correct. So what I'm going to do now is I'm going to switch to MATLAB. Okay, so this is something what we did for the inverse kinematics. So for the inverse kinematics, my first H01 was shown over here. This is the H01 that we found out. H02, H12 is this guy that we found out. And H23, the homogeneous transformation at the joint 2, 3 was this guy. Now, then what we do is we multiply H01, H02, H12 and H23. So that gives me H03. And let's do this calculation. Now, what we get is H03 is a big expression. So what I'm going to do is, in this big expression, I'm going to grab the Px, Py, and Pz's. So in this big expression, I'm going to grab Px, Py, and Pz's. And let's see what Px is. This whole big thing is my Px. So Px is equal to this guy. Then Py is equal to this guy. And Pz is equal to this guy. So my Px, Py, Pz are these. So now I'm going to use the command Jacobian. Jacobian. In the parentheses, square bracket Px, comma Py, comma Pz, comma. Now the joint variables are T1, T2, and D3. So once you have this, I'm gonna go ahead. I made a mistake here. This needs to be the square bracket, and here it needs to be the parentheses. Okay. So when you do this, this is the big Jacobian that you got. And you are welcome to check this Jacobian using the manual calculation, or you can just use MATLAB or any other symbolic software to verify if this Jacobian is correct. Okay, X1 was the other way. All right. So what I'm going to do is, so I need to change my direction of X1. That means my Z1 was flipped too. I'll make that correction in just a second. So everyone clear about this solution? Any question here? And please note, I just have to be clear that the coordinate system has to be consistent. If your coordinate systems are not consistent, your answers would be incorrect. So what does this mean? is this solution, when we worked out, we assumed the coordinate system to be in the different direction. So I should be seeing my screen. Just a second. Yeah, you should be seeing my screen here. So here is a small correction. And just to be clear, the equations were derived for this setup. So it was like this. So x1 was in this direction, x1, and sorry, this is c1 was in this direction, z1 was in this direction, and x1 was in this direction. So make this correction in this z1 and x1. So the solution that we worked out, z1 was the same. Let me see. Did I x1? So z1, x1, and how? What about, oh, y1 was up? Correct. Okay, that makes sense. Okay, y1. Okay, so this is the coordinate system that we used earlier. And please note, to find the Jacobian, we have to use the same consistent coordinate system, or our answers would be incorrect. So now next part is we need to find out omega x, omega y, and omega z. So this is problem 2. So this is problem 1. So to find omega x, omega y, omega z, omega x, omega y, omega z, I would have 0, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, theta 1 dot. Now, please note, the good news is we already have 0 R1, and 0 R1 is cosine theta 1, 0 sine theta 1, sine theta 1, 0 minus cosine theta 1, 0, 1, 0. And here the joint variable is 0, 0, theta 2 dot. So when you multiply, this equation is going to look like 0, 0, theta 1 dot plus, here let's perform this multiplication, sine theta 1, theta 2 dot minus cosine theta 1, theta 2 dot, and the last term is 0. So omega x, omega y, omega z. Now I need to formulate the Jacobian, which means this expression needs to be expressed as the matrix vector equation omega x, omega y, omega z is equal to, I'm going to have, for the sake of discussion, let me just write this. This will be theta 1 dot, theta 2 dot, So this expression is going to be 0, 1, 0, 1, 0. This will be 0, 0, and then I'm gonna have sine theta 2, sine theta 1 minus cosine theta 1. So when you multiply these, you will get the exact same expression. So you see this expression, which is expression 3, and this expression 4 is matrix vector form of equation 3. And that is how you would work this problem out. Okay, so before I go any further, just make sure that this is the exact same coordinate system for x1, y1, and z1 that we used when we worked out the inverse kinematics problem. Because the homogeneous transformations that we are using are corresponding to this robot in this particular coordinate frame. And with this coordinate frame, we got these rotational matrices and the homogeneous transformation. And finally, we got the Jacobian. Everyone clear about this? So, okay. The point, I don't have my original solution, but please note that you need to be in the consistent coordinate frame. Then you should be able to get the answer. If there are some issues with the coordinate frame, uh, I'm sure that you'll be able to correct it, and then you'll be able to get the answer. So let me work out one more problem. This problem is on the spherical wrist. So check this. So spherical wrist. So we looked at the spherical wrist problem, and the spherical wrist problem wherein you have 3 revolute joints which are perpendicular to each other. So you have this revolute joint that is perpendicular to this revolute joint, and then finally you have this revolute joint. So you have 3 revolute joints that are perpendicular to each other. And I just want to tell you, I will just quickly write down the matrices that we derived. And this is what we derived in the class in the earlier lessons. So we derived 0h1. 0h1 was cosine theta 1, 0, sine theta 1, 0, sine theta 1, 0, minus cosine theta 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. Now please note, in this matrix, this guy is 0 or 1. The next matrix that we derived is 1, H2. In 1h2, I have minus sine theta 2, 0 cosine theta 2, cosine theta 2, 0 sine theta 2, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0. Please note, this guy is 1R2, and I also derived 2H3, and this 2H3 is cosine theta 3 minus sine theta 3, 0, 0, sine theta 3, cosine theta 3, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And this guy is 2R3. Remember the spherical wrist? We actually drew the kinematic diagram in this orientation. I think this was the lesson before DH parameters. So something like this. And then we set up the equations, and we found these three homogeneous transformations. Now, please note, if I were to do, and this is very interesting to observe, if I were to do 0H3, which is 0H1, 1H2, 2H3, I would get a matrix. But the last column of this matrix will be 0, 0, 0, 1. So you are going to have, if you look at the solution, what this tells me is Px is equal to 0, Py is equal to 0, Pz is equal to 0. And the reason for that is we are assuming the distances between the revolute joints. So this revolute joint, this distance is approximately 0. The distance between this revolute joint and maybe this revolute joint is approximately 0. They are very close to each other. So which means there is no linear velocity, but please recognize there is angular velocity, which means in this case, we have to find out the Jacobian of the angular velocity. So to find angular velocity Jacobian, omega x, omega y, omega z, 0 r 0. Please note there are three joints. So 0, 0, theta 1 dot. Then there is a second joint which is 0 r 1, which is 0, 0, theta 2 dot. And the last joint is 0 r 2, which is 0, 0, theta 3 dot. Please note, and I want you to look at this. We know this guy is an identity matrix. So I don't see any problem here. 0, 0, 1, 0, 0, 0, 1. This guy, please note that this guy we already know. So 0 r 0 is known. So this guy is known. So this guy is known. But this guy 0 r 2 is not known. So this guy needs to be found out with an expression 0 r 1, 1 r 2. So this guy needs to be found out. So to solve this problem, I need 0R1, and that needs to be multiplied with 1R2. Everyone understood this? Now I'm going to switch to MATLAB and work out the problem. So I'm going to go to MATLAB. I'm going to share my screen. And now you should be seeing my screen. And what I'm going to do is I'm going to define SYMS, T1, that is theta 1, T2, that is theta 2, T3, that is theta 3. And I'm going to say R 01. I don't need to find out H01. R01 is cosine T1, 0 sine T1, sine T1, 0 minus cosine T1, comma 0 1 0 0 0 0. Oh no, 0 0. So this is, then I would have R 1 2 is equal to minus sine T2, 0 cosine T2, cosine T2, 0 sine T2, 0 1 0. So just for the sake of confirmation, now I would say R 0 2 is equal to R 0 1 multiplied by R 1 2. So I want you to check my the transformation matrices. So my first transformation matrix is correct. My second transformation matrix seems correct, and my third transformation matrix, which is R02, is the product of these two guys. Now what I'm gonna do is I'm gonna go back to my whiteboard screen and use this information. So here, if I want to work out this problem, I have omega x, omega y, omega z. I will have 1 0 0 0 1 0 0 0 1 0 0 theta 1 dot plus 0 R1. We already know cosine theta 1, 0 sine theta 1, sine theta 1, 0 minus cosine theta 1, 0 1 0, and this guy will be multiplied with 0 0 theta 2 dot plus there will be last term and I'm going to need more space for this. So I'm going to write it over here. And this is going to be cosine theta 1, sine theta 2, sine theta 1, cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2, cosine theta 1, cosine theta 2, sine theta 1, cosine theta 2, 0, sine theta 2, multiplied by 0, 0, theta 3 dot. And what needs to happen is you will have to perform this multiplication, and then finally you have to write this equation in a vector matrix form: omega x, omega y, omega z is equal to the Jacobian multiplied by theta 1 dot, theta 2 dot, and theta 3 dot. So that is how you find the Jacobian. And I want to ask you if there are any questions at this point. And I see a question from Travis that about the direction. So please check if my direction are consistent. It's possible that I might have made a mistake, but the idea is once you have the forward kinematics, you can actually grab the values of px, py, pz and find the Jacobian. And I want to emphasize in this particular lesson on finding the angular velocity Jacobian, where you will have to find out the rotation matrices with respect to the 0th frame. Yeah, it's a really long answer. Do you want me to find it using MATLAB? Yes. There is funny thing. There is a MATLAB command for collection of similar terms, which is called collect. So you can use that command and actually simplify the expression and write that in the matrix vector form. Okay, so what I'm going to do is I am going to switch back to MATLAB. Okay, now what we have is we need to find out the angular velocity Jacobian. To find angular velocity Jacobian. And to do that, I'm gonna use some other symbolic variables, SYMS. I'm gonna call d theta 1, that signifies delta theta 1, delta theta 2, and then delta theta 3. So these are, and the final answer is going to be something like this. Identity matrix. So J omega is equal to identity matrix 3 multiplied by 0, 0 dt1 transpose plus R01 multiplied by 0, 0 dt2 plus R02 multiplied by 0, 0 dt3. And please note that these are vectors, so don't forget to transpose them. So I multiplied by and I will start. So this is my answer. I's R01, R02, and this. So let me write this down. So I'm gonna actually there is something in MATLAB is doing conjugation. I don't want MATLAB to be doing conjugation. Let me check something real quick. Oh, it does conjugation. So let me see. Okay. Okay. So rather than transposing the vector, this is the command that you should be using. So this is my Jacobian, and I'm going to switch back to the white screen. So if you here is what I did. I use the command JW is equal to EYE3. This actually gets you an identity matrix, 3 by 3 identity matrix. Now here is something else that is super important. Since we are using the symbolic variables, I specified my vector like this, T1. So this is actually a vector. So what this is doing is 1 0 0 0 1 0 0 0 1, and this is 0 0 dt1. Plus I have R01 multiplied by same thing plus R02 multiplied by 0 0 dt3. And that, once I am done with all that, it gives me the answer sine theta 1 dt2, so which is theta 2 dot plus cosine theta 1 cosine theta 2 theta 3 dot, which is omega x omega y as cosine theta 2 cosine theta 1 theta 3 dot minus cosine theta 1 theta 2 dot omega z is theta 1 dot plus theta 3 dot sine theta 2. And if you want to write this at the Jacobian, this equation is going to be like 0 sine theta 1 cosine theta 1 cosine theta 2, then 0 minus cosine theta 1 cosine theta 2 sine theta 1, and then 1 0 sine theta 2, theta 1 dot theta 2 dot theta 3 dot, and this is the angular velocity Jacobian. Okay, I'm going to stop here and we will look at the alternate formulation for the Jacobian and the static force analysis in next class.